So we got this thing. We want to basically identify all the stuff that we can get from the graph. Again, there's a little bit of setup stuff about assuming that the degree is as small as possible and that the leading coefficient's either positive or -1. Again, this is all basically just saying that like what we see on the graph is what's actually going on. There's not some, like I'm not trying to trick somebody or whatever. We want to identify the zeros, meaning x-intercepts, along with their multiplicities, the sign of the leading coefficient, and then write the function in factored form. As part of that, I'm gonna write down the degree also. But so here's this graph. Again, we're assuming that what you see is what you get here. That like everything that happens here is what it appears to be. What can we say about it? Just right off the bat, what do you got? Okay, positive leading coefficient. Why? Yeah. It ends pointing upward, which means that the leading coefficient is going to be positive. Again, the problem said, like, let's assume it's +1 then, right? Okay, an odd degree because the ends go in opposite directions. Okay, so leading coefficient is positive, and that's because it ends pointing up. And the degree is, okay, odd, because the ends go in opposite directions. If we're assuming it's as small as it could possibly be, what is the degree here? 3. Why 3? There's 2 turning points, which means it's got to be at least 3. And it has to be odd. Okay, well, 3 is odd and at least 3. So if we're assuming it's as small as possible and not like secretly 17 or something, and I just hid some stuff in there, then we can say the degree is 3. Okay, what are these zeros? -2 and 4. I know the copy came out kind of small, but -2 and 4, that's where it intersects the x-axis. Okay, and then the other thing we can say about the zeros is that every zero of a function has an associated multiplicity that tells us something about how the function behaves. So based on what we see here, what's the multiplicity of that 0 at -2? Why 1? Yeah, the fact that this just crosses straight through. If I kind of think about zooming in right here, if I only look at this, that pretty much looks like a straight line. That means the multiplicity that like locally that thing's almost linear, which means its multiplicity is 1. Okay, what's different about 4 though? At 4, the function kind of bounces off of the x-axis. Or again, if I want to think about this locally, what does it do idea? It looks like a little parabola right there, right? Which means its multiplicity is 2. Really means the multiplicity is even, but we're assuming things are as small as they can be, so 2 then. Fun fact, what do you notice when you add up the multiplicities? You get the degree, yeah. Okay, and then the last thing we can do is write down this function in factored form. Write the function in factored form. So the whole thing here is that for polynomials, this is not getting, we'll lean on some more today and into next week too, but zeros correspond to factors. So if x equals a is a 0 of the function, then x minus a is a factored function. Yeah. So provided it's only got real zeros, which is the only thing that we're gonna like deal with, then yes. Yeah. So the real answer is no. The practical answer for stuff you can see is yes. Which is kind of how every question like that goes for the whole thing. Yeah. So factors and zeros go together. If this has a 0 at -2, then what does the corresponding factor look like? X plus 2. The idea being that if I take this and separate it out and set it equal to 0 and solve, to solve that, I move -2 over by subtracting, which causes that like sign change, right? And that's why the generic thing I wrote down is x minus a. Okay, the other factor would be x minus 4. The other stuff we need to fix are the leading coefficient. It's positive, so I don't really need that, but for emphasis, if you want to write a plus out there, for that leading coefficient being +1. Again, don't really need that, but that's why I wrote it in a different color. X plus 2, x minus 4. What about these? Multiplicity tells you how many times that factor shows up. So this being multiplicity 1 means its factor only appears one time, which means I don't need to write a power on it. This one, though, shows up twice. So I write it as x minus 4 squared. Then we ought to be able to, check some stuff. Even if I only want to do a rough check, x times x squared does give me x cubed. So what I thought about the degree matches. If you wanted a more thorough check, I could actually graph this thing and see if it matches the graph that we started with. Now, one thing to be aware of there is notice that I didn't give a scale on the y-axis here because, I may have adjusted the graph to make it kind of fit better and look nicer, right? So if I graph this on a calculator, oops, in the like standard, viewing window, it may not look exactly the same, right? I may need to, zoom out a little bit or something. But the thing I'm looking for is that the shape matches, right? This goes up, it turns around, it comes back down, bounces off the x-axis, and the intercepts look right. If we, a little more carefully do the zooming stuff, I can get the thing to look pretty much the same. But that's how we can check. All right. Okay. Y'all tell me about this one then. There's just no way to get this stuff to fit. Degree is 4 or what? Okay, there are 3 turning points. You have to go up, you have to go one more than that. So the degree's got to be at least 4. What else tells me about the degree? Leading coefficient's negative from the end behavior. The other thing the end behavior tells us, these go the same direction, so the degree's got to be even because they go the same way. Yeah, good. Okay, so the degree's got to be even, and it's got to be 4 or bigger, right? So 4 is an even number, so the smallest it could possibly be is 4. And the leading coefficient's got to be negative. Yes. This part tells me that the leading coefficient's negative. Right? The last time I see the graph as it, disappears off into infinity, it's pointing downward. And hopefully you saw it. Did I send an email or did I just post it? I think I just posted it. You guys get told when things get posted anyway, though, right? The Blackboard. The thing about how to sort of translate the in behavior thing. As x goes to positive infinity, y, the function values are going to negative infinity. So in other words, pointing downward. Okay, what are these zeros? -4, -2, and 5. 1, 2, 3. There, okay. And what are their multiplicities? 1, 1, 1. There we go, sorry. 1 and 2. 2. Just make it, I don't know. Okay. Everybody agree? And again, we said the degree was 4, the multiplicities add to 4. That's, kind of a good sign. So what does this function look like in factored form? It needs a negative out in front for the leading coefficient. The factors are x plus 4, x plus 2, and x minus 5, and that one gets squared. Yeah. Multiplicity 1, so it's good enough for the factors to just show up. Same with this. This one's squared, though, because it's multiplicity is 2. Okay, cool. In case it shows up in homework or something, because, you know, those are randomly generated, so I don't know what every version of the problem looks like, but if a function does something like this, the fact that it's crossing means that the multiplicity is odd, right? So multiplicity is kind of like, again, a like zoomed in microcosm of the end behavior idea. So locally here, the ends are going in opposite directions. That means its multiplicity is odd. But because this is sort of leveling out or flattening out as it crosses, locally, that looks kind of like a cubic, right? So this would mean that the multiplicity here would be odd, but something bigger than 1. So if we're assuming things are as small as possible, that'd be multiplicity. So basically, the kind of pictures that we need to have in mind, I'm going to draw a better version of this. He said, challenging himself. These are kind of the 3 types of things we can see multiplicity-wise. This looks like a little parabola inside that circle. Its multiplicity is 2. This looks like a straight line. Its multiplicity is 1. This looks like a cubic. Its multiplicity is 3. Or some odd number higher than 3, but we're going to assume things are as small as possible, right? So like the difference between multiplicity being 3 and 5 or 9 or 11 or whatever, you can't really see a difference in that. You can see a difference between 3 and 1 though, right? 1 is just going to go straight through. Higher odd numbers are going to kind of flatten out like that. Okay, and again, I don't know if, you know, whether this will actually show up in homework or whatever, but that's how it goes. Okay, cool. We feel good about that? Questions about things? Good. Okay. All right. Well, the rest of this week then, today and tomorrow, we're talking about solving equations. Okay, here's a whole bunch of stuff from sometime in the past. Solving quadratics, which are the family of degree 2 polynomials. To solve quadratics, we had a few options. We could factor and apply the zero product property. We could complete the square. And apply the square root property, right? Take a square root of both sides and you get a plus or minus, and then you work through the details. Or we can make sure we get the thing to standard form. And what am I trying to write? Sorry, quadratic formula. That's how you solve quadratics, right? Which are all the degree 2 polynomials. Well, now we're talking about solving higher degree things. So if you look at some of the stuff here in, we're in example 6 on the last page of the notes. You look at some of these things. I've got cubes and 4th power things showing up. And some of these are factored to begin with, but if you think about expanding, that's a cubic. This is a degree 4. So we're talking about, solving equations and seeing what we can apply from stuff we already know to solving these higher degree things. So for starters, I'm just going to turn you loose on A and B. Okay, so what can we do on those first couple? We've got one thing times another thing times a third thing, but they are equal to 0. So we have a product that's equal to 0. And anytime you multiply things, whether it's 2 things or 3 things or a million things, if you multiply stuff together and get 0, the only possibilities are that one of the factors, or more, I guess, but one of them had to be 0. So the options are that either this is 0 or this is 0, or you get the idea, right? Okay. So the possibilities are that x minus 7 could be 0, or x plus 12 could be 0, or 3x plus 2 could be 0, which means that the solutions are x equals 7, x equals negative 12, 3x is negative 2, so x is negative 2/3. Right? Okay. Really what we're doing is the same thing that we were doing with the graph just a few minutes ago, right? And Tuesday. We've got a factored form of a thing. Solving this equation is another way of saying find the zeros or find the x-intercepts of that function, right? Well, if it's already factored, then this is just a matter of splitting up the factors, setting them equal to 0 individually, and then working out what x value would make that true. Okay. The same thing is going to be true on B then, right? So we should almost be able to just look at this and write down what the solutions are, right? What are they? If this is 0, then x is negative 1. If this is 0, then x would be 3. Or if this is 0, then x is 5. And the square kind of doesn't really matter. It means it's a repeated root or it's got multiplicity too, but it doesn't change the value of what makes that thing 0, right? The only way to zero out this term is if x is 5, 5 minus 5 is 0, 0 squared is still 0, 0 times a bunch of other stuff, who cares what it is still going to be 0, right? Okay, so if the thing is factored, we can still do this, right? We can still use factoring and the zero product property idea to split things up, to simplify, to solve. The problem, of course, is that we don't always start with things that are already nicely factored for us, right? Another potential problem would be that if I had something like this and it was equal to, say, 1 instead of 0, this whole thing falls apart. Like none of this works anymore because this is about 0 products, not about products that are 1, right? You multiply stuff together and get 1. I don't know anything about anything. So this only works in the specific case where we've got a product equal to 0 because, again, it's right there in the name. Okay, cool. Well, that means that one option would be, to try to figure out a way to factor. We've got all of our usual factoring sort of skills, right? We can look for common factors. We can try to do the like trinomial factoring, A times C and add to B thing. We could maybe, if we really wanted to, don't necessarily have to, but we could maybe lean into this graph idea and try to use that to help us get through it. The unfortunate things are that completing the square works because quadratics are degree 2 and degree 2 things are square, right? So like really what's going on kind of under the hood in completing the square is a geometric argument about, rectangles and squares and sort of like adding pieces back on to turn one into the other. What that means is that when you go up to degree 3, now you're talking about a cube instead, and the geometric thing gets a lot more complicated. You can still do it, but like it's not something that we want any part of. So we kind of lose that then if we're talking about higher degree stuff. And, all reliable, the quadratic formula, that comes from completing the square and just kind of grinding it out with A's and B's and C's and figuring out what that would be. Which means that gets more complicated too. There is a cubic formula. This is what it looks like. And this actually only gives you one of the 3 roots, and then you have to use some other methods that we'll talk about later on to find the other 2. But this is a mess, right? I mean, it's again just A, B's, and C's. There are D's in here too because you've got 4 terms now. But I mean, it's the same basic idea. You peel the coefficients off, you push them into this, and it tells you what they are. But like, I'm certainly not going to try to memorize this or anything, right? Because it's a mess. Like, no one wants that. If we go up to degree 4, like this is the degree 4 formula. Now it's 4 separate lines for the 4 solutions, but like it's stuff like the thing we just looked at, but all the way across here, right? I mean, look how tiny that font has to get. And like, just, I don't know, zoom in on some part of it, right? In the denominator, like this is not good, right? Yeah, it's kind of a whole thing. Like we sort of take it for granted, but for about like 200 years, maybe even a little longer, like this was the thing. Like finding roots of polynomials was a thing. And like in Italy, in the like Renaissance universities, mathematicians would like throw down and like you'd like roll into town and be like, I want to be the professor at the university. So you'd go to the guy who is the professor and be like, I challenge you to a duel. And they would have like a weird math duel about solving stuff. And whoever won would like then kind of have the job because, they're the best. And the other guy would kind of get run out of town. And I don't know, it's weird. Like it's a whole weird sort of point in history. But yeah, pretty much. Yeah, I rolled up and threw down. But anyway, we kind of lose the general formula thing, which means we're going to have to lean more on the factoring idea. So let's just jump into it. X cubed minus 3x squared minus 18x equals 0. Now, a lot of these, the thing we're going to have to do to start with is notice something, right? What's backwards? Okay, why is it backwards?
Because
Oh. Okay.
it's actually not backwards. I don't know.
Okay, it's either backwards or not backwards, but in either case, what do we see that might be helpful? Okay, that's good. This is a good start. Because if it's equal to 0, then if I can factor, I can solve, right? If we can factor, we're good. I don't know how to draw a thumbs up. Oh, no, we're just going to forget that happened. If we can factor, we're good. Okay. So then the question is, can we factor? Yeah? What can we factor? Okay, so two things. One, there's a common factor of x all the way across. That's good. Common factors can come out. So if I factor x out of everything, what's left? X squared minus 3x minus 18. Hey, what kind of thing is that? It's quadratic. What do we know about solving quadratics? Everything. Thank you. You knew the answer to the question before I even normally I got to train people on the what do we know about solving quadratics thing. What do we know about solving quadratics? Everything, right? Maybe you can factor it. Can we find a pair of numbers that multiply to negative 18 and add to negative 3? Yeah, we can. That'll factor. Even if it didn't factor, though, it's quadratic. How do you solve any old quadratic in the whole universe that I throw at you, even if it doesn't factor? And you got a quadratic formula, right? Yeah. Quadratic formula is, sort of small enough that I can store that in my head and carry it around and work with it. So this one does factor, so we can do that. Now there's that factor x sitting outside. That's an 8. What multiplies to negative 18 and adds to negative 3? Negative 6 and 3. So this becomes x minus 6 and x plus 3. Now we have a fully factored thing, right? I've got these 3 separate pieces that are joined together by multiplication. It's equal to 0, which means the zero product property applies. I might keep being obnoxious and actually writing that down for a reason. That's a 0. Kind of looks like a weird backward 6. So what are the solutions then? And 0. This common factor of x that we took out in the first place is still there, right? It still counts. If x was 0, then these would all be 0 and 0 equals 0, right? Okay. Those all had a common factor. When we took that common factor out of everything, it reduced this degree 3 cubic thing to a quadratic, and we know everything about solving quadratics. What two? Oh, on where? B? Yeah, right. Okay. So that's a factor in the thing, right? But if you split those up and set them equal to 0, does 2 equal 0? No, so that doesn't go anywhere. The others, though, x plus 1, x is a variable, right? So that can be made to equal 0 if x is negative 1. So that's why that factor kind of doesn't go anywhere, right? It doesn't do anything for us. The others do, though. Yeah. Yeah, it's a good question. And that's how the common factor that we took out here, x, that's different because that can take on different values. So that could be 0. If it was 0, it would kill the whole thing up. 0 the whole thing. Okay, so that's, number one thing to look for. Are there common factors? And that's just true in general anytime you're trying to factor a thing. If there's a common factor all the way across, we take it out, life gets easier, we go on from there. Pretty good? Yeah, all right. Okay, well, you'll notice these are kind of in pairs, and they're in pairs because the ones that are, next door are going to be fairly similar. So I'm going to leave this one for you. You do this. Oh, I spelled you wrong. You do this later. What if there's no common factor? And again, like, let's try to put ourselves in, not, it's the day that we're talking about this in class, but, this shows up on the test question or out in the wild or some weird Italian man in one of those fluffy Renaissance collar things shows up and throws a problem at me. This is cubic, degree 3, so I don't have a formula for it. I do see that it's equal to 0. That's still a good thing. If I start running down my, options though, I'm trying to factor. But if I look all the way across here, I don't see a common factor. Okay, what can we try instead? Any ideas? Do what? Break it up how? Okay. Okay. What points us toward doing that? Because it works? Okay, yeah, fine, fair enough. Okay, there are no factors all the way across. But if we break it up, we might be able to find some factors within the smaller pieces, right? Now for this one, like these being the same, kind of jumps out at me. We'll look at another way to think about this in a second, but what do x cubed and x squared have in common? They're both multiples of x. How many can we take out? 2. So x squared. If I take x squared out of both of those, what's left? X minus 1. Right? The idea is that, I should be able to distribute back and get this back, right? So x squared times x squared times -1. What do these have in common? 64. Okay. Because of this minus sign here, I'm going to write that as minus 64. If I take negative 64 out of negative 64x, what's left behind? Just the x. If I take negative 64 out of plus 64, what's left is minus 1. Still equal to 0. Okay, now I've kind of got these two big pieces, right, where there's multiplication going on. This is positive, but I took minus 64 out here. So when I distribute that back, I need the two negatives to, cancel, right? And the reason I did that will make more sense in just a second. Yeah, we'll see. Like, I did it because it works, but we'll see why it works in a second. Now, the thing to notice here is not that this is x minus 1, but that those are identical, right? They're exactly the same. So if I have these two pieces, x squared times pink thing minus 64 times pink thing, what do they have in common? They have that in common, right? They each have a factor of whatever is under that, pink squiggly thing that I blocked out. If I take that out, what's left here? X squared. And what's left here would be minus 64. Oh, hey. We factored it. I know, right? It feels like we just sort of fell into it, right? Like we backed into factoring the thing, but it's factored now. This is called factoring by grouping. We'll walk back through what we did here, and then I'll show you like another way we can kind of think about it. Okay, so I see these four terms with nothing common all the way across, but because there are four of them, I can kind of pair them off, right? So x cubed and x squared, just because they're next to each other, right? And look for things in common to those. X cubed and x squared have x squared in common. Okay, take it out and this is left. Do the same thing here. They have 64 in common for sure, so I can take 64 out. What would be left is an x and a 1. For this part to work, I need these to match. That's why I factored out negative 64, so that what would be left would be x and negative 1, so that these would be identical. So that's why I like forced that to happen, so that those will match, because when those match, I can take it out like a common factor. Here it is. And then what's left behind is x squared and minus 64. I think I've circled too many things and it's maybe not that useful anymore. But what comes out of this term when I take out x minus 1 is this. And what comes out of this one is this. Because, so for the same reason that when we took x squared out of this, what's left is just whatever you need to, like, think about distributing it back and sort of working back up. X squared times x would be x cubed, right? X minus 1 times this thing. Go ahead and multiply that back out. X times x squared would be x cubed. X times negative 64 would be minus 64x. So I've done the first and the outer parts of the product. The inner part of the product minus 1x squared. And then the last part will be plus 64, and that's what we started with, right? They're in different order, but we can move that around. So this is then this thing factored correctly, right? Factoring is always just, basically tricks or methods to split things up to be able to rewrite it. If multiplying it back out gets you where you started from, then you factored correctly. So this does work. This thing factored. Again, this is one way you can think through that, breaking them into pairs and looking for common factors within the pairs. Let me do that another way real quick. I know that I'm trying to factor this thing and I see four terms. So one thing I could do is just say, well, hey, maybe this comes from doing a binomial expansion like a FOIL type multiplication. And maybe I can just, kind of educated guess my way through what they're going to look like. To get x cubed, what can I put here and here? An x and an x squared, right? Okay, well, that would give me x cubed for the first part of that expansion. Okay, well, let's roll with that and see if we can get somewhere. Now, these middle two, we might need to be a little bit, fluid on which one's outer and which one's inner. But like the middle two need to be these two things. But, it kind of matters. Which one's outer or inner kind of depends on, what order I wrote those in. For one of the two products, I want to get negative x squared. I've got an x squared here. So what could I put here to make that, dream come true? Minus 1. Okay, so I've made my outer and inner sort of swap order, but that's okay. I want this to be negative 64x. I've got an x already. So what needs to go here? Minus 64. And then does that do the right thing for the last part? Negative 1 times negative 64? Yeah, 64. Okay. The grouping idea, if we're, sort of comfortable with how, oh crap. If we're sort of comfortable with how that works, the grouping idea helps us through that. If this makes sense to you and you can get there, that's fine. I don't really care how you do it, just that you can. Then we can split up and solve. Okay, so for tomorrow, finish that one and do F also. So finish and do those. We'll talk about the last thing tomorrow and look at inequalities too. All right, y'all have a good day. I'll see you tomorrow.